So just like in chapter 13, we can compare the values of the QSP and KSP to see if a reaction has reached equilibrium. And if it hasn't reached equilibrium, which net direction it will progress until it does. So that means we can use the solutions of soluble salts that contain ions of slightly soluble salts, and then we can calculate the ion concentrations and predict the result when we mix those solutions together. So for example, if we were to take all of these different ions and mix them together, will they form a precipitate? So if we had our chlorine, our sodium plus, our 2F minus, and Ca2 plus, and they were all mixed into this overall Erlenmeyer flask here, what will happen? Well, what we'll see is that the Na plus and Cl minus do not react, but the 2F minus and the Ca2 plus can react to form CaF2, which is a solid, meaning they will be able to form a precipitate, and they'll continue to form this precipitate until the solution becomes saturated. So if you had initial amounts of all these different ions, specifically the ones that are going to form a precipitate, then you would be able to get a Q value. And then with that Q value, you will compare it to a known KSP value through one of the tables or an appendix, for example. Now, when you have a saturated solution, that QSP value that you calculated is going to equal to your KSP value. But when you have an unsaturated solution, your equilibrium is going to shift to the right. And so if it shifts to the right, that means it's shifting towards where all the ions are being formed. So for example, if I'm shifting towards this direction, I'm only producing Ca2 plus ions and 2F minus ions. And therefore, no precipitate is going to form. And so therefore, your QSP value should be lower than your KSP value after you do your calculation. And finally, you can have a supersaturated solution, which means that the equilibrium is going to shift to the left. And so if I'm shifting to the left, I'm producing mostly solids. And so you're going to be forming a lot more precipitate. And so therefore, your QSP value is usually going to be greater than your KSP value when you see this type of excess precipitation form. And of course, these shifts are going to occur until it goes back to equilibrium and becomes saturated again. So we have CaF2 Vision, who's going to represent a saturated CaF2 solution. So really, Vision has the ability to basically manipulate density. So of course, I'm like, he can manipulate density. He has the ability to manipulate solids, right? And how much solid is formed in, say, a saturated, unsaturated, or supersaturated version of this CaF2. And so that is a connection I made with Vision. So CaF2 Vision has the ability to manipulate density and, of course, be in equilibrium in saturated solution to form its individual ions. You can also take those ions and then shift back to the solid form if necessary, if there's any type of equilibrium changes. So let's go ahead and mix some ions and get into an example in the Avengers compound. This question is all about predicting whether a precipitate will form. It says a common laboratory method for preparing a precipitate is to mix solutions containing the component ion. Does the precipitate form when a 0.100 liter of a 0.3 molar calcium nitrate is mixed with a 0.200 liter of a 0.060 molar NaF solution? They gave us the CaF2, or the KSP of CaF2 is equal to 3.2 times 10 to the negative 11. So as we saw before, we need to get all of our ions together, and then we need to figure out which of these ions are going to form a precipitate. They kind of already gave us the work, or they've done the work for us, because since they already gave us the KSP value of CaF2, then we automatically know that calcium and fluorine are going to be the ions that cause a precipitate. We also just saw CaF2 Vision, so we also know that that's going to form a precipitate for sure. But let's go ahead and write out all of our particular ions, and then of course see which ones we're working with. All right, so as you can see, we have our CaNO3 So we know that NO3 minus is going to be the anion of that strong acid, or HNO3 Thor. So that's not going to react with anything. But yes, we do have our Ca2 plus left over. Finally, with NaF, we know that Na plus is going to be a part of that strong base, NaOH, so we definitely don't use that. You also could just remember NaOH Black Panther if you wanted to. And of course, that means what's left is going to be F minus. Therefore, we need to basically figure out and say, okay, if this Ca2 plus and this F minus is going to form precipitate, what precipitate will it form? It will form CaF2. And if that's the precipitate that is formed, then we definitely can write a dissolution equation. And we can go ahead and add our ions here, Ca2 plus and 2F minus. Now we have a dissolution equation that's already balanced, and we already know specifically which ions are going to be used. Since we already have our dissolution equation, I'm then going to write my KSP expression, which is equal to Ca2 plus multiplied by F minus squared, right? Then I go back to the problem. It says that we are mixing 0.100 liters of a 0.30 molar calcium nitrate solution with 0.200 liters of a 0.06 molar NaF solution. So the total volume at the end of all this mixing is going to be 0.300 liters. And then again, because I know I'm trying to focus on QSP versus KSP, I know I have to figure out my QSP amount. And so I do have to get the initial amount of my Ca2 plus and F minus. So to get my initial amount, I'm going to need the molarity, right? And so that's going to be my moles per liter. Now, again, what are my moles? I'm going to take my molarity given and multiply by the volume given specifically for Ca2 plus. When I multiply these two numbers, 0.1 times 0.3, I get 0.03 moles of Ca2 plus. Remember, I'm not focused on nitrate because Ca2 plus is the only one that contributes to solubility. I do the same thing with NaF. I take 0.200 liters times 0.060 molar of NaF, and I get 0.012 moles of F minus. Why am I only focused on F minus? It's the only thing that contributes to solubility. So now I have the amount of moles for them. If I want to get my concentration of Ca2 plus, initially, I'm going to have to take my amount of moles, which is 0.03 moles, and divide it by my total volume, which is 0.300 liters. I'm going to do the same thing with F minus to get my initial amount. So I get my initial amount of Ca2 plus. Again, it's 0.03 divided by 0.300 liters, and I get 0.100 molar. I do the same thing for F minus. I get 0.012 moles divided by 0.300 liters, and I get 0.040 molar, okay? Now, my QSP expression is going to be similar to my KSP expression. I have my Ca2 plus multiplied by F minus squared. So now I'm going to plug in my values here. I have 0.10 molar multiplied by 0.040 squared. So when I take my 0.040 squared, I get 0.0016. I'm going to then multiply that by 0.1, and I get 1.6 times 10 to the negative 4. Now it's time to compare, folks. This is our comparing time. And when I compare, as I can see, my QSP value is way larger than my KSP value, which is very, very small. So when they ask me, does a precipitate form? The answer is going to be yes, a precipitate will form. And how long will it form? It's going to form until it reaches that KSP value of 3.2 times 10 to the negative 11. Once that's reached, we're back to it being a saturated solution, right, folks? But because QSP is larger than KSP, we call this solution here supersaturated until it reaches saturation. All right, on to the next concept.